I think it's recording. Yep.
Okay, excellent. So I think the first, this is the second time we've done this type of meeting. The first meeting was pretty structured with 3 talks and then a little bit of time at the end for questions. This one is hopefully going to be a bit of a flip where myself and Taylor are going to give sort of walkthroughs of pipelines of using tedana with AFNI and then fMRI prep. And then we'll hopefully have a larger time for questions and discussion at the end, and maybe more time for sort of thinking about, this community and going forward as well. And we will see how it goes. So I will say that one of the big requests we've had was just sort of a run through of the pipelines and how people actually use the program. So what I'm going to do is a demo run through of the script I would do to run tedana with AFNI, and I'll sort of visualize, verbally narrate myself looking at the results to give people a sense of that. And then Taylor will do the same, and we can have questions as we go or at the end of these two. So here we go. So 1 second, what's going on? Did the slides get reorganized somehow? I don't know. We'll find out. So this is the entire AFNI pipeline to go from essentially your data off the scanner to statistics. It's primarily this command called AFNI proc for those of you who don't use AFNI. And don't worry that it's very small. I'm going to go through it bit by bit. I'm not going to explain it all. There's actually bigger tutorials for that, but just kind of giving you a sense of how to orient what this looks like. So the very beginning of AFNI proc is you're telling it what steps you're going to run. So we're going to despike the data, we're going to do slice time correction, motion correction and alignment of the epi to the anatomical, motion correction, mask outside the brain, both using the fMRI and anatomical data. Combine is the step that says we're going to run combining echoes in some way. So you're giving it multiple data and combining it. You're scaling by the mean per voxel, and then you're running your GLM regression. This first chunk of stuff is all the information in the anatomical, so it's the name of my file. I'm also saying that I've already calculated a lateral ventricle mask and a white matter mask that I'm going to use later. Here's the fMRI files, so we can see, there's 3 runs of this data set. It's a flash and checkerboard block design task, 3 runs for echo 1, echo 2, echo 3. And then finally, you have to give it the echo times, which will pass to tedana. You're going to say, when you're doing motion correction, use the first echo, which is our current recommendation, because it seems to be the less corrupted by T2 star signal and better for alignment and stuff. And in this data set, there was a non-steady state volumes at the beginning, so we're removing the first 4 volumes. This is sort of general AFNI stuff. This is the commands to align the fMRI to the anatomical. So what cost function to use, which image to align, and how to correct. Now, this next step is really the key addition when you're using it with tedana, which is you have this combine method call. And in this case, I'm using m_tedana. And what that means is AFNI is going to call whatever tedana is in your path. So if you have version 25 in your path, it's going to run version 25. If you have version 23 in your path, it's going to run version 23. And then you can also pass options to tedana with this one. So I'm saying start with 45 initial components from PCA. I'm going to use the minimal decision tree, and I'm running robust ICA, which means it's going to run ICA multiple times and find a common signal. And I'll say for this data set, this robust ICA and the PCA step is something we can discuss much later on, but sometimes the automated methods for component estimation seem to be too high or too low on this data set. And it's a 150 volume data set, and it always seems to end up being slightly below 45. So I'm so far finding that using an initial and just saying, give me 45 PCA components and running robust ICA works well with this data set. So that's this phase. And I'll note that the combined method here is mTedana, which is the one I just said, which is just use Tedana in your path and take the denoised time series. One of the philosophical positions of AFNI as a pipeline is it gives you a lot of flexibility to do what you want. So it means that you have a lot of options. You have to think through the options, but depending what you want to do, there's a lot of different things that you can do. There, other packages like fMRI Prep do give you some flexibility, but they're also sort of pushing a bit more towards best practices. And I'm sure Taylor's gonna, the best option. Taylor's gonna, push back on this later a little bit. But what that means is you have freedom to try a lot of things. So mTedana is the method I'm using here. You could also do mTedana OC, which means just run Tedana for the optimally combined data. You can run it and say, run Tedana, take the orthogonalized regressors and put those into your GLM and then let AFNI regress out the regressors. And there are some benefits from and this is sort of taking the denoised data and regressing out again. This helps make sure you're getting the correct number of degrees of freedom, but it's a bit slower. You can also say take the optimally combined data from Tedana and use what Tedana is regressing and just do that step in AFNI. That should be nearly identical to what you'd get by just doing denoise and AFNI in Tedana, but gives you better degrees of freedom, and then you just have one regression step together. And you can even use AFNI for optimally combined and then use Tedana just for regression. So there's all these options, and I'm sure every one of these has existed, was made because on some sort of use case that someone brought up. And we can, at various points discuss which one might be right for each study. And this is just going through again. These are options for regression. You can, decide if you're going to censor. I'm going to be adding the motion and first derivative motion into my GLM. This is a checkerboard task where they're pressing a button a few times. So we have the checkerboard and the button press. And this is sort of just and we're also regressing our white matter regressors and lateral ventricle regressors. Oh, sorry. Task design, regressing white matter and ventricle. And then finally, in AFNI Proc, there's this BIDS derivative option, which says AFNI has its own file naming format for a while. But if you want to throw this into BIDS, you can just add BIDS derivative yes, and it's going to save everything, the key files that BIDS likes with BIDS style file naming. And I'm passing it these uvar commands to say, use session is session 01 because AFNI didn't really just inputs a subject, so this gives a bit more info. And finally, it can open a quality check report to look at it. So I'm going to show you the quality check report for this first subject. I'm going to go a little bit fast through just the AFNI parts, but just to give you a sense of what's here. And then we'll focus a bit more on the Tedana part. So AFNI is just showing you this is what the raw fMRI data looks like. This is what the raw anatomical, I gave it a skull stripped image. This is the overlay before you do alignment. This is the overlay. This is essentially the epi as an underlay and the edges of the anatomical, and you can look and see how good your alignment is. We have this is the mask. This says these are the boxes with data. So you can see on this data set, I am missing a bit of the frontal lobe and a bit of the cerebellum and a bit of the brainstem. So if those were areas that I cared about, that would be an issue. Now these are the statistics after all denoising. So this is the F-stat of my block design checkerboard task. And I can see, does it look like where we expect brain activity? I can click this button and open knee view right in here and explore more. So it's like I said, it's a visual checkerboard task. So we got really robust visual response. We also, if I move around, have somewhere around here. There's responses everywhere, but we get a bit of response in motor cortex to signal the button press as well. So this is roughly what I expect it to look like. If I wanted to, I can click this other button and open the entire AFNI terminal. So I'm just seeing my two contrasts here. I'm seeing the motion correction parameters here, and these red lines are where it's censored. So you can see this is a relatively low motion volunteer across 3 runs. Again, more motion parameter information. This is the carpet plot from Global Signal. And now I will open and in here they just sort of, Tedana has its own QC report, so you can just click on this and open the QC report right there. So, ooh, that's weird. I don't know why it's appearing up there. But what we could see, maybe it's just the width of the window. Yeah, okay.
It's definitely the width, yeah.
Yeah, I didn't know it doesn't, but anyway. So this is what we can see is about, in this run, about half the variance was accepted, half was rejected. Ooh, lovely live demoing. So I can click around the components and see which ones are accepted. I could see some of these look plausibly good. This one, we're seeing visual cortex activation in some of them. One thing I'm noting is I definitely see my task in some of these, but none of these are sort of robustly showing the clean block design on the individual trial. I can also look here and say, these are the value, this bottom right quadrant is values above the kappa elbow and below the row elbow. So those are most of the ones accepted with the minimal tree. Here's one that has a slightly higher kappa value. And if I look at it, I'm definitively seeing task in it, but I'm also seeing a linear drift. Because these are my 5 blocks of the checkerboard task. So what this tells me is this component probably contains a bit of both. So it's better to, I'm glad it's being kept. But that's just what the ICA gives out. But it's noteworthy that there is some noise. Hopefully this noise might just be removed from detrending as well later on. And if people haven't seen, you can look at each of these components. You can see some of the key values, the variance explained. Oh, we just added in version 25, this variance explained by rejected, which I'm not sure you can view through the share. But what this is saying is this component, if you look at the rejected time series, 63% of the variance in this component are also in rejected time series. So that says that even though we're accepting it, it includes a lot of information that's in rejected time series as well. And if we orthogonalized rejected, actually a lot of that would end up being kept. And this one is, 30% is overlapping with rejected. So you can see there's some variation, and I think it's a good measure to sort of see this component is only 25% variance explained by rejected. So it's much more signal. So it's another number we just threw into the program that I think might help interpret a little bit more what's happening here and there. Like I said, I ran robust ICA. And what robust ICA is showing, and this is sort of a quality check for robust ICA. So ICA is run 30 times, and then it makes these clusters. So if you zoom into a cluster, you can see that 30 iterations all appeared in the same place in this 2D space. But if you look at, but there are some clusters that were sort of did not cluster. So every one of these clusters became one of the components across the iterations, and they'll be much more stable, but it gives you a sense of what it looks like. So if you're seeing, wider clusters and circles that cover a lot more, or things, the reds are the ones that didn't end up in a cluster for an iteration. If they look weird, that's something else to think about.
Dan, you
Yes.
have a question in the
Oh,
chat.
okay.
So Nelson is asking if it is considered good or acceptable to have half of the variance accepted.
For this, I think it's fine. I mean, clearly what's happening here in this case is there's one component that's about, well, actually it says this is 18% of the total variance, which is a mix of signal and noise. So in an ideal world, ICA would parse this into 2 separate components, one with pure signal and one with pure noise, but it didn't. Because ICA is designed to parse the data based on spatial independence, and not parsing the data based on cap and row. So we know this has signal in it, so we should not remove it. But it is an issue. So maybe if you look at this later and say, is the noise here mostly that linear drift, or is something else? But it is what it is. So you can flag it and say, I definitely don't want to remove this component, but I should know that this component is a strong mix. And on balance, it's going to give us better signal, but we don't want to remove something that contains robust task information. Did that answer the question? I'll also note for some reason, however I have Zoom set up right now, I am not seeing Maybe I can open it.
Yes, that did answer the question. Thank you.
Now I am opening the chat. Okay. Okay. And some of this is covered in our documentation, but we are given the base mask, which is red, which almost always is completely overlapping with the green mask, which is the optimal combination mask. So I don't see any red line at all. And you can see that the adaptive mask is looking for voxels with at least 3 good echoes, and that's what's being used for ICA. So your output is going to be everything within the green mask. But ICA is going to be done only on the voxels within the magenta mask for classification. And you can see in this case, most of the voxels are there. We're also outputting this. This is sort of the T2 star map that's being used for calculating the weighting for the optimal combination. And it looks like a low resolution T2 star map with some dropout here. So that's roughly, I think this is a fine one. There's others, sometimes we see things weird. We're also showing the S0 map, which should have kind of the edge artifacts if you are having many small quails on the surface. I think this is something we added about 9 months ago that's quite useful, in that this is the fit to this T2 star and S0 model by voxel that's used for optimal combination. Areas at the bottom of the brain with the dropout, the higher is worse. So redder is worse here. And here, I'm seeing the worse areas in dropout regions and other things on the edges, so I'm not too worried about that. But if you're seeing dropout other places as well, that might be a bit more concerning. And I think that's it for the report.
You have another question now.
Question, yes.
From Ali.
Okay. Does the so before manual checking data post processing based on individual runs. So right now, I personally think it's good to manually check. My personal approach is, unless something is flagrantly wrong, I do not make any custom changes, because you want something that is, you don't want sort of like human judgment biasing your results. But if you see something clearly wrong, you can change it manually. The other thing I would say is, if you have a data set where you're repeatedly seeing things wrong, it's possible to adjust the decision tree to, for whatever aspect of your data makes the thing fail all the time. I think the much more elegant approach would be run the decision tree, tweak your decision tree so that doesn't happen. And I think multiple people on this team would help someone if that's the issue. I would also say, now that we have things like this T2 star map and these mean T2 star values, these might be very useful tools for saying, let's say you're doing a study of hundreds of data sets, and you're skimming them, but you're not, multiple people looking at that. Some of these numbers might be useful for flagging outliers. So if your root mean square error for your T2 star fit is what is this, 120 for most of your subjects, and in a few subjects it's 300, that's a sign those are the ones you should prioritize looking at manually and seeing if something's going wrong. And in that case, the issue isn't the decision tree. The issue is there's something wrong with your data. And I think more likely than not, tweakings of the decision tree are going to be less essential than flagging data sets that have more substantial issues. Okay. And I don't think I need to go through the rest of the AFNI output. There's some stuff there. But the other thing I wanted to highlight is we've run tedana we can now add external regressors directly into tedana and do fits there. So for the AFNI perspective, it's not currently built into the pipeline, but AFNI proc outputs a script with all the subcommands it runs, and it's actually relatively easy to pull out the relevant sections and rerun it with external regressors. And I'll note that when I showed you the script before, I calculated ROIs for white matter and lateral ventricles for CSF. And because Afni calculated those regressors, I can put those right into a rerun of tedana. So that's what I am doing here. So this first script, which when these slides are shared later, you'll be able to see and look more carefully, is just something that takes the outputs from that first iteration of Afni proc. It gives the headers that tedana is going to expect, and it's going to make a single regressor file per run that's going to have the motion time series, the first derivative motion time series. So that's 12 regressors. It's going to have 3 regressors for the lateral ventricles, and it's going to have oh, it is the white matter to this one, but just CSF, lateral ventricles. And I also am adding the task design, so button press and checkerboard, which are expected. And then I am running tedana, where this file that was generated is now added as an external regressors. And I'm also using the exact same mixing matrix I previously calculated, because especially with robust ICA, you're going to get almost the identical result the second time, so we don't have to waste time rerunning the mixing matrix. So to actually get through the tedana step, it is pretty easy to make this code. Every so often I poke the Afni team to make it a bit more automated, but this is where we are now. And then the next step is I copied and pasted from the Afni proc to essentially, after tedana is run, I am, in this case, I'm pulling there's a command to essentially lets you pull the orthogonalized mixing matrix from tedana of just the rejected time series and generate the time series to reject. And then you can rerun, you can scale the images. And then this is the GLM step in Afni, where now note here, instead of adding the motion regressors, which I added before, since I fit motion to tedana, I can just add the component time series that tedana says reject, and that should include the key motion ones that are fit by the data. And that's it for that one. The one thing I'll show now is I pre-opened the exact same one with external regressors. So one thing I'll point here, so this is the one without external regressors, this is the one with. And one thing I noticed here is you can see a few components here that were rejected before and were previously accepted. And one of them is this component 8. Where is it? Component 8 is there. So component 8, and this is kind of the opposite question. So like the current decision tree for external regressors is a bit of a work in progress. So this was the accepted component, and we can see the exact same component here was rejected. And one thing we've now added lower down into this, when you run external regressors, we get this matrix of how well each external regressor fit to that component's time series, and how well it fit to sort of all of them together, the motion ones, the CSF ones, and task. And what we can see is component 8 fit the task pretty well, but below the threshold, but also robustly fit to motion and CSF and really fit to noise. Now, I will say, just like I was saying before, we should keep, I'm looking at this one. This is a high kappa value, a low rho value, and it is right in visual cortex. So just like I said, you should keep this one even though there's noise. I would say this one is a mistake. You shouldn't have rejected this one. And in this case, the external regressors, it's called demo because this tree is a work in progress and tweaking. So if you're playing with external regressors, I strongly recommend looking a bit more carefully at the things that change. And tweak these. Ideally tweak the parameters. So maybe right now we're saying keep if it fits your task more than r squared equals 0.5. Maybe I should have tweaked this and said, if it's 20% task, you should have kept. So that's just one example of what to do there. So, and Rick had a comment. He's from the Afni team. And I want to make sure to give time enough for Taylor and questions. So that's where I am. Do we want any questions before Taylor starts his part? Okay.
All right. Cool. Thanks, Dan. Um, my part is not nearly so detailed or interactive. Apologies. Um, Here I have outlined the basic steps that so I guess I should start by saying fMRI prep is a minimal preprocessing pipeline, which means that it is meant or it's designed to do the basic steps that are pretty consistent across packages or across workflows that are part of preprocessing. That includes slice timing correction, motion correction, susceptibility distortion correction, co-registration of the functional data to an anatomical reference, and then normalization to target spaces like MNI or, FSLR CIFTs. Um, as part of the workflow for multi-echo data, it will apply Tadana's T2 SMAP workflow to to calculate T2 star S naught and do the optimal combination across echoes, which is then the optimally combined data are then what is passed out of the fMRI prep workflow in whatever target spaces you want. There is a flag called ME output echoes that will output the minimally preprocessed individual echo files. These have gone through slice timing correction, motion correction, and susceptibility to distortion correction, but not any kind of co-registration or normalization to a standard space. So this is what I recommend people pass into fMRI or to Tadana after running fMRI prep. What you have to do is you have to collect these preprocessed echoes produced by fMRI prep, remove any non-steady state volumes from the preprocessed echoes, and then run Tadana on those adjusted ones. If you have external regressors, you will need to remove the non-steady state volumes from those as well. But you can pass them in, typically by just grabbing the fMRI prep confounds file that's produced, remove those leading few rows from the file, and then use that in conjunction with an external confound config file that will work for fMRI prep confounds. Once you're done with that, you can add the non-steady state volumes as just lines of zeros back to the Tadana mixing matrix, and then denoise the fMRI prep outputs in whatever output space you want with that mixing matrix and classification table. We have example code in the Tadana documentation for different kinds of denoising, like aggressive, non-aggressive, and orthogonalized aggressive. That's all in Python, but should be doable with AFNI or ICA reclassify or whatever you want as well. So I guess I can pull up some Python code that I use to run Tadana on fMRI prep derivatives if I have share access. And it seems like I do. All right, awesome. So this is a short function that I used in a recent data descriptor manuscript to run Tadana on some multi-echo data. It takes in the raw data set, the fMRI prep directory. This also combines fMRI or Tadana with fMRI post aroma. You can just ignore those elements if you want, but I wanted to see if it worked well in conjunction with ICA aroma, which it seems to, as well as a temporary directory and an output directory for the Tadana derivatives. So to start, I just find each of the run's first echo from the fMRI prep derivatives right here, and then I essentially loop over those. From there, I just I adjust the glob and find all of the echoes for that run. And then Then I also grab the fMRI prep mask because we want to pass in a brain mask that's pre-computed rather than relying on tedana's mask generation function, which is, as users have mentioned, not particularly great. So we grab that mask. I also grab the confounds file from fMRI prep in order to find out which volumes are non-steady state. So it automatically infers that here, and then I convert that to a single integer. And I start, well, I'll scroll ahead a little bit. I start removing the non-steady state volumes from the fMRI prep EchoWise files here. Basically, I just load it up, remove those volumes, and then save it back out as a temporary file, which I then pass into Tedana down below. In this particular case, I'm also loading the mixing matrix from ICA Aroma, but that's probably not a common use case. From there, it'll run Tedana and you'll get out the HTML reports that Dan walked through before, not the AFNI ones, just the Tedana ones. And you can grab those and pass them, or grab the outputs from Tedana and pass them along to denoise your data. All right. Dan, you want to pull back up your screen?
While Dan does that, Taylor, you have a couple of questions. Yeah.
Oh, totally. Okay. So from Nelson, oh, there are a few questions regarding denoising after Tadana. What are our recommendations specifically on should we only use Tadana components in denoising? Should we include motion confounds? Oh, things jumped around a little bit. One sec. Should we only use or should we include motion confounds? Should we include any components from a comp core? And should we use global signal regression? Oh, all right. Well, I think all of us probably have different opinions to some extent. I mean, optimally, I would like to combine Tadana with rapid tide as opposed to global signal regression. I think that rapid tide is a more principled approach to removing the physiological noise that global signal kind of gets at. Yeah, I think that's what I would say. In that particular example, I did include global signal at the request of my PI. So, you know, uh, do whatever you think is best, I guess. I think including motion regressors as external regressors is probably better than including them as additional confounds, like Dan did in his example. I think that's a really great way to do it.
Yeah.
Um,
I'll I'll add to that one on the motion stuff. My ideal is we have 12 motion regressors usually, and some people do even more, and that results in a lot of loss of degrees of freedom. In theory, if you run ICA and you find the ICA components that actually represent those 12 regressors, you might actually only have to remove 3 or 4 time series based on motion. So I think that's the goal, but how to actually do that and how to set our thresholds is still a work in progress. And I think the more people that try this and play with this, the better we'll be able to sort of find best practices. But I think that's what I want my goal to be, but I don't think we don't have the best practices yet. Um, and for global signal, I'll just, say no, but ever. But that's a longer discussion.
totally. Uh, for ACOM core as well, in my opinion, it's certainly better than global signal regression. I think including those ACOM core regressors in the decision tree would be optimal. We haven't figured that one out, or we haven't tried that out yet, but I think that would be a good thing to look into. Uh, and that's another thing where I think rapid tide specifically would be a useful substitute. Basile has, with the new fit apply scheme, is it possible to use ME output echoes on already preprocessed data in an apply pass if you didn't do it before? I That's probably a better question for Chris Markevich, but I think so. I think that should work. If it doesn't, then I'm betting it's worth opening an issue to the fMRI prep repo, and then uh, I'm sure that the devs would want to implement that because it seems like a very useful addition. Um, I'm sorry if I butcher your name, Nayun. What is the difference between using tedana on AFNI versus fMRI prep? Um, None. I mean, tedana is getting run the same way uh, internally. The AFNI and fMRI prep, I don't know the exact step where AFNI applies tedana. That's probably a Dan question. But in fMRI prep, you would do this after slice timing, motion correction, and susceptibility distortion correction. So the idea there is that minimal changes have been made to the data that might affect the scaling across echoes. Um, I think the same principle applies to AFNI proc.
Yeah, I think that, yeah, it's going to be the same. So it's essentially after you've done everything on the three echoes separately. Um, I'd say I kind of hinted at this earlier. The other, and I mean, underlying fMRI prep does even use some AFNI commands for large parts of this. So it's your decisions for what you do in those earlier steps. So fMRI prep mostly centers on a few options. AFNI gives you a lot more rope to play around with, and also possibly you know get yourself in trouble. But I think AFNI definitely just in general has a bit more flexibility on every step of the way, and it can actually and also integrates the denoising step into its main pipeline as opposed to sort of running it and then doing it a little bit separately, except for the external regressors like I just mentioned. So I think conceptually they're very similar, but sort of how you run them and what you prioritize is slightly different.
And also, just, I mean, software implementations always have weird differences. So fMRI prep uses McFlirt instead of 3D Volreg for motion correction. I think the choice was basically arbitrary on fMRI prep's part, but there have been a number of papers that have shown that like even with the same interpolation and cost functions and stuff, you're going to get slightly different results. So there will be drift even if you're like trying to make sure everything's exactly the same. And I don't think that that necessarily reflects problems. I think there's just an element of analytic flexibility or researcher degrees of freedom um, that should be accounted for.
It's also occurring to me, I think I'm not the fMRI prep user in case you couldn't tell. I think fMRI prep essentially builds in a version of tedana into each version of fMRI prep. So like it's a bit more static, where in AFNI you can, pull the newest version and it'll just run whatever you have, which again is more rope. So you can be it's a little bit easier to be on the cutting edge within the pipeline, but also it's a little bit easier to end up running different versions on different data sets in a study if you're not careful.
I will note that with due respect to the analogy of rope and flexibility, there is a large amount of provenance that goes in the AFNI proc, so you can be sure of what you've run because the AFNI version, the software versions are output. You get the processing script so you can see everything that you did. And I do think sometimes people do like being able to choose their analysis. I think even with fMRI prep, you can choose different software and some different steps that you use. So
And I'll add with all the quality check measures in AFNI, when you do blow things up by messing things up, it lets you know. So it's much harder if you bother to look at the QC stuff. It is much harder to make a big mistake and not notice it. I mean, it's hard. I shouldn't say much harder. It's hard to make big mistakes and not notice something's wrong.
So, uh, all right, the next one was Nelson. In my data set, I have seen that significant physiological noise is present in the final FC maps when I use only tedonic components for denoising, but I am unsure if it's correct to use ACOM core and GSR here. Um, yeah, I think we spoke to, you know, I mean, I won't endorse GSR either, period. But including ACOM core as separate regressors, you you're probably reducing your degrees of freedom in the output a little bit, but until we have a decision tree that really works well with ACOMP core regressors and we know the right thresholds that will apply across data sets, that seems totally reasonable to me. And that seems to be the end of the unanswered questions.
I'll note that in fMRI you can do ROI-based PC regression, which should be like a comp core, and along with the motion, I can look at passing some of those to tedana, if that's the direction you guys wanted to go.
If I'm not mistaken, ACOMP core just means you have regions that you take PCs of principal components of and then pass those principal components in. Is that right?
Yeah, anatomical comp core. So the anatomical regions, which there are specific ways that that I think you're supposed to do it. That fMRI prep tries to do it that way. Like you should erode your white matter and CSF masks before you do this, so that way you're not getting any gray matter bleed in. But yeah, I think that's the basic approach.
Yeah, I'll note that's pretty much exactly what I did in my demo, except I forgot to put the white matter in the rerun. The only quirk is because you want to calculate those on the optimally combined, there's this sort of there's sort of this double step that you got to sort of get your optimally combined, then calculate those regional averages, and then feed it into tedana. So that's, thinking of all the pipelines, it's a little bit of a jump step right now, but if it's the way we're going, we can probably speak to both pipeline teams and figure out a way to make that more efficient.
I would also, in terms of like the difference in software, there's both the cases that the same thing is sometimes, well, I guess it's more that the same thing is called different words in each case. So censoring and scrubbing might be a famous case. When we talk about running principal components of regions, yeah, we erode them and that too. So I think there are times where sometimes the difference is really the phraseology. It's not always the case, and there are other things too, but that is certainly a challenge in using different softwares. But again, that's only kind of a question away that can be asked too.
So I think we're done with the current live chat questions, but I sort of also threw at the end these prompts to sort of, some of these we've covered already, but some of these are new, but we are just, welcoming questions on current stuff and visioning. So how to look at quality reports, how to automate scale. I mean, these are things we're hitting already, and might be, more focused topics for future ones. Better ways to use it than the PC issue, which is kind of still hovering over us. So, well, if people want to prompt more on these questions or their own, that's fully welcome now. Yeah, 2020. The new fit to the rejected regressors was added just a month ago, so it's in version 25.
Was that part of the release, or is it just in main?
It's in the release.
Okay. Looks like we have about 10 minutes. Yeah, I was about to ask if you were going to move over to the next one. Yeah.
I mean, this is now free form, but like there's also just, there's the current questions of how we're using it, but there's also just visioning. So there's what enhancements do you would really help people, ideas for the methods and better in general, not just with tedana. And also what are, if we actually cleared all our open pull requests a few weeks ago, which was a first ever. So there's stuff on our to-do lists, but we also have the opportunity to sort of think about like, what does the community need most? So if people have priorities or things they really want to see, or if they personally want to contribute to things, now is actually a good time to sort of think about which directions to go. And I'll also mention that we've been talking a little bit more about improving online educational resources for multi-echo in general. So if people have ideas of what they want to see or what they want to help with, I'd love to talk. And I see Rick raising his actual person hand. So yes, Rick.
IRL. So there's still two things I would like to still consider for tedana. Um, for example, in that one regressor that was like in the visual cortex, but had that large drift component, in the context of external regressors, it might be nice to get some of the decision making orthogonalized to things like drift and possibly even censoring. If you know you're going to censor time points, that's a lot of variance from a head motion that you're trying to fight with using tedana. And similarly for drift, that's a lot of variance just for some smooth curve that you could take out of the data and possibly get more refined computations afterwards, you know.
I
Uh,
think
we've definitely discussed that before. And it's on the long list, but maybe that could be one of the higher things. I think adding in they're both a little bit tricky in practice because when you remove drift, it's going to affect what PCA and ICA does, and we want to make sure we don't break anything. And censoring is very doable. It's going to hit a lot of the code, but the one open question is because we're regressing things out, we kind of have to zero out everything censored at that point to keep the time structure, unless people have other ideas of how to interpolate areas censored out, because we don't want people to sort of not denoise time points within tedana and then use that stuff later. So
Can you use the pointwise censoring, just spike regressors?
maybe I should talk more with you about the different ways you've approached that.
The PCA is done on the OC data, is it not?
Um,
So if that's the
Yes,
case,
yes.
the OC data you could slightly clean before getting your making your decisions, possibly.
mhm.
we have played around with that in the past. I tried detrending before ICA or PCA, and ICA stopped converging on most of my test data sets.
Hmm.
I'm sure I wasn't doing it in a very in the best way possible. So I'm sure that there are ways to do it better, but some like ad hoc thrown together tests, stuff started failing real quick.
Thank you.
Are there any other priorities for people? Oh, Colleen?
I had a question, actually for you, Taylor. I think at the end you were talking about the output spaces, and I remember for a long time, I don't know if recently it's changed, there was a note saying, we don't know if you should do this in like scanner space and then transform the optionally combined denoise files, or do it in template space and then run it through Tadana. So I was wondering if there are any thoughts or kind of, I know that was untested for a while. Um, if there was any sort of new insight about that.
Um, so I think one element that is related, but it's not it's distinct, that we really weren't sure about, and we're a bit more concerned about, was whether what transform should be applied before Tadana, right? The big one was should we do distortion correction before Tadana? And
Oh, yeah, yeah.
practice, it didn't seem to have a major effect. Um, so that's something we were like genuinely concerned about, I think, in terms of whether you should warp your data after denoising or denoise data that has already been warped. Um, I think that they should be and I think the people who really study transforms and stuff, Rick and Paul, will be able to speak to this better than I can. But I think that they should be roughly the same. Because fMRI prep outputs the optimally combined data in whatever output space you want, I think it's just simpler and easier to denoise that data, um, instead of doing like tedana and then warping tedana to other things, especially if you want to denoise SIFTs, because
Mm.
the process is just tedious to go, from the bold ref space, the native space data to the SIFT. Rick's raising his hand though, so.
Yes, so our general thought on that is if the subjects are like if it's a mouse or something, if it's a subject that can't move, then you're probably wanting to stay more in original space and preserve that quality of voxel accuracy. But if it's a human analysis in general, subjects are bouncing all over the place relative to a voxel size. Uh, Once they move a third of a voxel, original space is gone. Just the motion correction
Mhm.
alone, you're already off the grid. So we figure it's nicer just to go straight to standard space with a small caveat. Well, either way, either space. In the case of Tedana, we usually use more of a Fourier interpolant, a sync interpolant, rather than
Okay.
just like a cubic or something like that, just to preserve the edges a little more, preserve the regions a little more sharply, it seems to.
Yeah, that's a really interesting point about motion and how to and when to transform these things. I work with older adults
Mhm.
who love to move. I don't know if they love it, but they move quite
Yeah.
a bit. And so we've been playing with, when we do task analyses, group GLMs, we standardize to a template. But if we're doing something like resting state connectivity, we tend to keep people in T1 space and then parcelate them kind of individually. So there's all sorts of questions about like for different use cases, we either normalize or don't, but we're always dealing with motion, distortion correction, et cetera. So that's
Sure.
that's a interesting point to think about when those transforms make sense. And then also once you do it, like if you keep it in T1 space through and then sometimes do and don't normalize after. Cool.
I I'd add on, the issue I have seen, and it's been a few data sets, is if you have a data set that has a real intensity and homogeneity. So like, let's say you're using small receiver coils, so it's really, really bright on the surface and it drops off really rapidly to the center of the brain. Some of the nonlinear interpolation methods might mess with the relationship between your echoes. And I haven't like systematically seen this to say like it's an issue with all data sets, but that's been my concern. And I've sort of seen anecdotal hints of that concern here and there. And what that means is if you're doing alignment that really benefits from the, non-linear, like, the sync interpolation or fancier things, it could cause an issue, but I don't know if this is a universal problem, and the benefits of saying you're just doing one spatial transform on your data are substantial. So at this point, I'm leaning towards if you can only do one spatial transform, do what you can and Tedana will deal. But if you're seeing something where, you're suddenly seeing in the center of the brain, your third echo has larger magnitude than your first echo, that's the sign that there might be something bad going on that relates to this interpolation issues.
Thanks. That's really useful.
It's got a question if people use Nordic and Tedana and how much that has an effect because it is such it's a pre-PCA over little patches and things.
I know Rob Smith in Australia is very interested in that. So I think the idea that we had planned was to essentially disable the PCA step for dimensionality reduction and just go straight to ICA. Does that sound familiar in Echo and Dan?
So Rob Smith scoop. I mean, they're using not Nordic, they're using MPPCA.
Yeah, but
But it's a very conceptually very similar, and they seem to get it working. There's a manuscript under review right now on that one. I think other people have played with Nordic, and in theory, they should blend very well, but sort of Nordic is changing the assumptions that go into tedana and ICA in general. So I think there's a bunch of people have just sort of hit run and given it a try, and it messes with the assumptions. So and it causes problems. So we have to sort of give it a bit more thought. I mean, frankly, with multi-echo information, we should be able to do what Nordic does 100 times better, because we have one additional measure of what's thermal noise and what's not. So that is a wonderful thesis project, possibly.
Yeah,
even.
actually, I think one of Cesar's students was
Yes.
working on that,
Yeah.
but I don't know how much progress he's made.
Hydra, yeah.
Yes. Yeah.
Rob Smith has also been working on it. He one of the enhancements to DWI noise that he's been working on is applying MAPCA, no, MPPCA to data concatenated in I think he concatenates in the like a fifth dimension across echoes rather than Hydra, which uses the data concatenated in the like Z concatenated, I believe. Um, so there's a few avenues people are pursuing. Whether that, how that translates to Dana, I think is still also up in the air.
I think if Cesar or at least people at BCBL were fairly happy with Nordic and Tedana in combination. I haven't heard from them in a while though, so you would have to ask them directly, Paul.
So there's a new question on checking motion during the scanner. Um, I I know, like, when you use AFNI real time at the scanner, which not many people have set up on their sites, it will automatically calculate motion parameters. I know the group that does FIRM is using multi-echo, so I wouldn't be surprised if they have it included. But if they haven't and you make a feature request, I assume it's near the pike, coming down soon.
Yeah, they've been big proponents of the 5 echo protocol that we're also using at Penn. So I would hope that they have firm supporting that.
Actually, I think Firm does work with multi-echo. If I remember correctly, Stefano used it for his big data collection.
One general question for the people still here. It's past noon, but the first meeting, like I said, we were very structured and was mostly 3 talks. This meeting was a bit more free form and a bit more time for Q&A. I think we're probably going to keep bouncing around different styles for different meetings. But I'm curious if there's anyone who has feedback on, what they want to see more of in future of these meetings. And our next meeting is, we should have some sort of meetup for anyone who ends up at HBM. I will be there. I'm not, and I think of the tedana developer team, the core team, I think I might be the only one there. But beyond that, there's probably going to be the next one of these meetings, and I think we said September is the goal. So if people have thoughts, feel free to write out directly or comment now.
Ali has another question.
Okay.
Is there a general idea of the potentially expected sum of the variances explained by bold components we may consider acceptable or that we need to keep in mind?
I'd answer that and say this is where motion comes into play. So if you have a massive amount of head motion, then a large amount of variance should be rejected. So if you have a volunteer that has less artifacts that we want removed, more variance should be accepted. So if you're seeing, if you have 2 subjects that everything looks good and there's very low head motion and nothing else looks weird, and one of them is accepting, 30% of the variance and one of them is accepting, 10%, that might be a sign something's going on. But just in general, subjects with high motion, also linear drift. Like if you have a lot of linear drift and head motion, a greater percentage is going to be rejected. So I don't think there's a general rule, but if you summarize these across your whole study, you might be able to say, the ones where there's, a lower, an outlier percentage of accepted are the ones you want to take a look at and say if there's something weird going on there.
Yeah, I can speak to that kind of as a user, having done this on a couple different data sets, young and old adults, and uh high risk for Alzheimer's data set, also high motion and all these things. Like looks very different, apnea, fMRI or apnea versus tedana because of some of the selection versus Prantix original code. So I think all these suggestions, like just look at the spread of your data and in your data set, like who are outliers, and like looking at the components is really the best way to QC. This is the question I get asked most by my collaborators when I'm helping them like look at multi-echo data is, nobody knows in single echo what's good quality. So I really echo this, like echo repeat this suggestion of look at the distribution of any of these metrics in your data, figure out the weird people and figure out why they're weird. And if you have a good spread of stuff, then kind of play with these options. I really love these external regressors, that addition. I haven't played with it yet, but that was something that we were really struggling with trying to add CSF and white matter signals and avoiding GSR, but getting in there. So I just cannot echo that enough. Having played with this in a lot of data sets and seen how it works well and doesn't work well.
I'll also mention as a future idea, I think there's going to be a lot of time before we figure out how to really include external regressors in a decision tree. But there's a current functionality that we might be able to just share pretty easily, which is you could just tag stuff. So we can make it pretty easy to say if you're giving a bunch of or you can, anyone can do this. If you just sort of get rid of the change classification and just say tag components that correlate with motion, tag components that correlate to CSF, then even if you're using an existing decision tree, it would let you, immediately pull that data into your analysis and might help a lot with quality checking and other stuff. So maybe that's something we should add in.
Yeah, I think you had suggested this at one point as well, like just pull some of these like and maybe show people the distribution. Like maybe if you're working with one, I'm thinking of older alts, like just because those are my people, but pulling, like figuring out what are some key measures, pulling it and then kind of sharing those potentially. Like I know that's hard to figure out which measures are right and you don't want to give anybody a threshold, but it was really useful for me to see like how many components are people getting accepted or bold components, and like when I was finding it very different between Prantix and Tadana version 11. I was like, some of the criteria, like I'm from Nathan Sprang's lab as a postdoc, and it was like 10 components. And I was like, why? Why 10? And so everybody asked me, why 10 components? Like, why is that the threshold for good components? And that's a really great question. So anyway, I think potentially if there was some way to pull these metrics for your data set, it doesn't have to be in Tadana. Like I'm not saying develop this, but pull that and then share those across our group so that people get kind of a general sense. Maybe that would be useful. I don't know what the full scope of that would look like, but
We have a
I mean,
few
yeah, sorry.
initial ideas / attempts. I created an open multi-echo data repository where I've been trying to keep track of any truly like completely open, no like sign in or requests needed multi-echo data sets. My plan eventually was to run them all through fMRI Prep and AFNIPROC and upload the derivatives to like OpenNeuro along with Tadana. But obviously we haven't built that database yet. We haven't like run it. And so therefore we are lacking the distributions. But I think that would be a good starting point because we'd also have demographics from all those data sets and we could show, like MRI-QC has, what the distribution looks like when you account for age or sex or
yeah.
Amount of motion. And we also have an issue open about creating a curated database of ICA results and to identify where Tadana is going wrong. I think that's Something, just an idea we had that I don't think we ever actually pushed forward on, but it is something we could revisit.
Yeah.
I'll
Yeah,
also
that's
mention,
awesome.
yeah, more and more like these useful summary stats we've been saving in a JSON file. So anyone who wants to pull these numbers out for a group study, it should be relatively easy to pull them, but there are other useful numbers. So if any user finds that like, hey, they keep calculating, some other number on the side, and then compiling that, we can definitely just throw those numbers in so that it's more consistently calculated across everyone. So like we just recently, through this, total variance explained by rejected components and accepted components. Now that's being sort of centrally saved as a number in a file.
Yeah, that was
So-
hugely useful.
yeah.
Super appreciative that you guys
Yeah.
were pulling that, because when I was playing with the ICA options, which I'm not super savvy to, PCA, ICA, that
Yeah.
was like critical for helping me figure out like what seems stable or not stable. Thank you to everybody on Neurostars also.
Yeah.
Where
Definitely-
I've like have 30 message threads on what number of components is correct.
But definitely if people are sort of separately calculating summary stats from the output of tedana that we could just add in, open an issue or just let us know directly.
Awesome.
I think we might want to wrap up now. And if you have any questions, either save them for the next time or reach us on Neurostars or GitHub. Yeah.
Or Mattermost.
Or Mattermost. Yeah, if you're on Mattermost, that's true. I always forget about that one. We'll upload the video this week, I guess. And I don't know if Dan and Taylor, you will share the slides. Maybe.
Sure. Let me we can make a shareable link of the slides that you can put in the comments for the YouTube.
Sounds good.
Yeah.
Thank you, everyone.